Okay, so today we're going to move from oil flow equations, oil rate equations, to gas. For the time being, we're just going to talk about the reservoir rate equation for gas. We'll ultimately look at the gas rate equation for pipe flow from the wellbore to the surface. And then we'll combine the two, the reservoir and the tubing, together into something called, in the paper by Fetkovich, wellhead deliverability. That incorporates both the reservoir and the production tubing flow. But right now we're just going to talk about the reservoir rate equations. And gas as a commodity or as a resource in Norway is well, actually, I think we're maybe making more money off of gas today than we are of oil. I think that wasn't too long ago from when we went to being from being an oil nation to being a gas nation, and that's happened many places over the last 20 years. Qatar's a good example, where they were actually a very small oil-producing country in the Middle East, and they have the world's largest gas reservoir, the North Field. And now they're producing very large quantities of gas and exporting that around the world as a liquefied, for the most part, liquefied natural gas product. The first discovery in Norway, in the North Sea, was a gas field, gas condensate field called Cod. It was just prior to, if I don't have my history wrong, probably is, but it'll be close. The Cod field is in the Ekofisk area, but it's not a chalk formation. It's the only, I think, Ekofisk area field that's not chalk. It's a sandstone. It's a gas condensate. It's not very big, but it was developed. I'm not sure if it's still producing or not, but it could be. The Alba Shale, which is a even richer gas condensate, was discovered fairly early, developed. Is a chalk formation. There's another field that was not developed until quite much later. Also in chalk. I forgot the name. Right, I'll remember it here soon, I think. And then Frigg was the first big gas field development. That was really, I'm not sure when it started producing gas, but probably in the 1970s, maybe the early 80s. And it was a very high permeability, kind of traditional gas type reservoir. I think Elf was the operator, and I believe it's now abandoned. Water encroachment, the well started watering out, and then ultimately it was abandoned. Sleipner was an early discovery. It was both gas and condensate. It's still producing. It's the first gas cycling project, I think, in the North Sea, both UK and Norway. Gas cycling is where you have this extra value of the condensate we've talked about, and what you do is that you try to get a higher recovery of that by injecting usually produced gas into the reservoir, and it sweeps some of that extra condensate to the surface, so to speak. And so it was a quite successful, actually, gas cycling project in the Sleipner part of the Sleipner field. I was lucky enough when I first came to Norway to work on Cod, Alba Shale, and Sleipner as gas fields and gas condensate fields being developed in the late 70s, early 80s. And then the Troll field was discovered by Shell, I believe, and it's 45 TCF. I'm not sure what the numbers are now, but it's a very high permeability gas sand. And when it was discovered, they also found oil underlying it. It was like an oil thickness of I think around 5 meters to up to maybe as much as 20 and 30 meters. But because the gas resource was so large, the initial strategy and development plan of Shell and Statoil, this is kind of a black mark in their history book, they basically said that the oil could not be developed because it was in this thin zone. So we're talking about thicknesses on Tuesday, how thick is thick and how thin is thin. So 5 to 20 meters thick was not considered thick enough to develop it. It was kind of prior to the real use of horizontal well technology, so that they would have to go in and drill vertical wells, and then the gas would just come in and you wouldn't produce much oil. So the amount of oil is estimated to be about 5 billion barrels. And Norsk Hydro, this little oil company who no longer exists, was absorbed by Statoil some years back. They had some kind of maverick engineers. One of the guys, I think, who was fronting a lot of this idea to develop the oil was Professor von Goldfracht. He was one of the first reservoir engineering professors at this department. He wrote a book on natural fractured reservoirs. And I was also lucky enough to work as part of that team for 4 or 5 months in 1984, looking at the possibility of producing oil from the Troll field using horizontal wells. And they were not just on paper. They decided to, I guess, basically build the Petro-Jarl #1, which is, Petro-Jarl is one of the first FPSOs, floating production, whatever it is, stands for SO. FPSO, yeah. And for the Norwegians in the group, there's this rich guy who used to be a petroleum engineer, and there was no job for him when he got out of school, I think in the early 80s. Spetalen, I don't know, what's his first name? Yeah, Øystein Spetalen. He's a rich guy now, probably because he didn't get a job as a petroleum engineer. So you have to look at the upside. He did his thesis on the possibility of doing floating FPSO production. So they actually built the Petro-Jarl, and they did a 6-month pilot test. Drilled the well horizontally and did a pilot test, and it was a huge success. They paid for the FPSO, and I think they even maybe ran it for longer than 6 months and verified that this was like a to-do thing with so much oil there. And now there's, I think, almost 200 wells. And at one point, it was the largest oil-producing field in Norway. So that was the Troll. But now they're starting, and finally, Statoil and Shell get to sell their gas. They had to wait a while, only produce a billion or 2 barrels of oil, poor guys. And they are now starting to develop the gas field itself, delivering gas to Europe. Oskar was discovered, I think, in the 80s, if I remember right, maybe late 80s. It's very rich gas condensate. There's some parts of it that's oil, very high gas-oil ratio oil, but it's mainly gas, and that's closer to here. If you're not familiar with Norway, it's closer to Trondheim. And then the latest large field is the Ormen Lange field. It's a dry gas, basically a dry gas field. I think about the same size as Frigg. I'm not sure about all these numbers, but it's quite large, the Ormen Lange field, and it's been producing probably close to 10 years now. We used to do a class project in this class with the Ormen Lange when it was first coming in. So Norway is a gas nation, and a lot of the world produces a lot more gas today than it did, like when I got here, because the price of gas has gotten so much higher, so the value of it's so much higher, and it's used more in industry. And so gas is a big deal. It's getting bigger in Norway as we speak. So we're going to talk about the gas rate equation. We'll spend the rest of the semester talking about gas for the most part. And the recommended reading for the Easter vacation, since you guys are off next week for a long week. Officially, it doesn't start until, next Wednesday at noon? I probably won't see you guys on Tuesday. No, there's no lectures on Tuesday. It's the university shuts down all of next week. But if you need something to read, this is the paper I've mentioned to you before. And the title of it is Multi-Point Testing of Gas Wells, and by Michael Fetkovich. And today we're going to get to the reason why he has this first word in the title of the paper, multi-point. And it has to do with the fact that what I've been telling you about Darcy doesn't usually apply to gas wells. So Darcy's kind of an oversimplification often for gas wells. So we're going to talk about that. So, yeah, I think, any questions about gas or history or anything before we get started on the dry equations and stuff like that? Okay. Yeah.
Do you have like an onshore field?
Onshore? Yeah, there's no onshore production in Norway. Yeah. So, Swedes tried to drill into the hard rocks of Sweden a couple of times, but I think they just burned somebody's money. So, you know, theoretically, I guess it could be there. It's all hard rock pretty much in Norway. So there is some hard rock production around the world. There's some in Vietnam and kind of what they call basement production. Some quite large production of basement, which is basically hard rock with fractures and stuff in Vietnam and some other places in Asia that I know of. But they didn't find anything in Sweden. Mm-hmm.
Is there underground gas storage in Norway?
There's no underground gas storage in Norway, no. It'd have to be offshore. I'm not sure that it would be a bad idea. I mean, there's certainly some depleted gas reservoirs that could be used, I suppose, but I don't think there's any out there. No, not that I know of. There is in Europe for sure, many places in Europe, Germany for sure, and other places. Gas storage is where you produce gas. Well, you have usually an emptied gas reservoir that's been emptied, and then because it's a seasonal demand for gas, usually in the winter the highest demand, and then in the summer not so much demand. So that you basically, when there's a low demand, you keep producing the gas wells and you store them into a reservoir which is more centrally located in terms of distribution. So you kind of fill this emptied reservoir during the low season, and then when the high season comes, you've got all this excess gas ready to be produced. Usually it's a high permeability type reservoir. That's called gas storage. So it's an annual cyclic. You know, you inject in the summers and you produce in the winters. And Keith Coase, who I think I've mentioned about the reservoir simulation, I put his papers out. He was one of the early pioneers in modeling gas storage, together with Donald Katz at the University of Michigan. Yeah. But there's none in Norway per se that I think. Any other? No? Okay. So, so when it comes to gas, because of the lower viscosity, you can get in the same piece of rock much higher velocities than you would with a liquid, simply because of the viscosity difference. So what's characteristic of at least conventional gas reservoirs, which are probably, I'll call it conventional, maybe more than 10 millidarcies, certainly in the hundreds. And if you get into the Darcys, then you're going to have very high gas rates being produced, making lots of money, and the velocities are going to be very high, particularly near the wellbore. Okay, because we didn't talk about it, but if you look at the equations that we derive for velocity, basically velocity is equal to the rate over this 2 pi RH term, right? And basically that means that velocity is a function of radius. It's like inversely proportional. So you have your max velocities where? At are near the wellbore, right? So, and can get quite high relative to the velocities far away. And anything that happens near the wellbore is important because, you know, that's where a lot of the pressure drops going on. So it's important. So it ends up that because these high velocities, it's a little bit like pipe flow. Does anybody remember pipe flow? You know, Reynolds number, flow in pipe. Have you had that in? Yeah? Okay. So what kind of flow regimes do you have in pipe? If you flow very slow or you flow water, they call it laminar, right? So basically, they assume the streamlines, the water molecule or the gas molecule kind of flows along, the same streamline. It's not like hitting the walls and moving around and stuff. But if the velocity gets high enough, then you get this velocity, you get a different kind of flow regime, which is called turbulence. Yeah, and turbulence is like chaos. So you get more pressure drop because of the turbulent flow. If you don't remember the friction factor Reynolds number plot, but we're going to come back to that. But basically, you get more pressure drop because of the turbulent type flow than you do if it was laminar. And what did I tell you about the more pressure drop? The potentially more cost. Okay, it doesn't have to be. I was thinking about that this morning on the plane. I don't know why I wasn't just sleeping, but I was thinking about. I made the statement I think on Tuesday that if there's more pressure drop, you get more costs. Not necessarily so. I mean, because you might double the pressure drop from 1 psi to 2 psi, and who the hell cares? It doesn't have any effect. But if you have significant pressure drops that are increasing for any reason, then those significant pressure drops are going to cost you money. So it's an important thing. And it ends up that near the well, you get these extra pressure drops, which means it's going to cost you more money, or you're not going to be able to produce as much gas as you would like to because of those extra pressure drops. So it's a bad thing. And so when people like Muscat and Botzad and these other people in the, I don't know, when it was 20s, 30s, actually even in the late, I don't know, early 1900s, I think, there was a guy, a German, I think, and I never get the name spelled right. I'm just going to try. He's dead, so, how bad can it be, right, for the great-great-grandkids? So, Forchheimer, he was doing the same kind of things as Darcy, but he was doing it with gas, okay? And I don't know why he was doing it. He was trying to clean air or something. I'm not sure. Or maybe he was just a scientist. But he was doing this, flow of gas through porous media. And when he made these measurements, Darcy had kind of said that if you flow as a function of velocity and you look at the pressure drop across, let's say, a piece of rock, or he probably just had a plastic cylinder and put sand in it, closed the ends and flowed gas through it, basically found that this, this pressure drop, yeah, Darcy, you're doing okay, but then eventually what happened is that this thing started increasing like that. Okay, so this expected Darcy behavior of a straight line broke down. It's kind of a straight line. So somewhere around here, you're getting this extra pressure drop. And why? Well, the analogy that they used, and in Muscat's first book, I think, he actually translates this kind of data into a friction factor Reynolds number plot, which I'll show you here in a little bit. And so I think what Forchheimer did, I think he gave several equations in the actual paper. I don't know that I've ever read it completely, but he gave an alternative equation to the Darcy equation that described what he observed. Okay, and then a bunch of other people started observing the same thing. So his equation is that flowing horizontally is that you get that's the Darcy term, okay? But then this deviation from the Darcy, he used a quadratic. I think you might have had it to the power n, but it's quadratic is what everybody uses. So he had a velocity squared term, and again, as was for the first term, this being a fluid property, PVT property, and this being a rock property, this constant in front of the second term also had a fluid property, which was density, and a rock property, which we call beta. Okay, it's a rock property. And it has different names. One is high velocity term. Another is non-Darcy. Okay. There's a number of terms, but it's the beta term. It's the second. So it's a rock property. So a rock will have a given beta, just like it has a given permeability. Okay. And that described these measurements. And so if you want to know the permeability of a piece of rock, in theory, from the Darcy equation, if you only have the first term, you only need one measurement of velocity and pressure drop, right? Because it goes through zero. So you go out and you make a single measurement. I'll just put it in. I'll make this an actual measurement, okay? And then you can draw the straight line, and then from the slope of that, you get the permeability, right? That's all you need is a single point. And when you're out testing an oil well, which usually follows the Darcy equation, it's basically you can flow it with one rate and find the permeability. And that's often what's done, a single rate. They might have a couple of rates, but generally speaking, they just have a single rate. So they kind of get one pressure drop and one rate, and then they can calculate the permeability. But if you've got this Forchheimer, second degree equation, then now you're going to need, a couple of points, and maybe because data uncertainty, don't make good measurements. It's quadratic. Quadratic can fit a lot of weird data, okay? So you might basically need multiple data points to find, in a sense, what? K and beta. Okay, it's two constants in the quadratic equation. Now, theoretically, you only need 2 points, but you need them right. So you get 3 or 4 to take into account things maybe not ideal. That is why Dr. Fetkovich has this multi-point in the title. And that is the standard method that we test gas wells, is with a multi-rate. That's what it means by point, a multi-rate test. Typically 3 rates is standard, maybe 4 rates. Okay? And the whole purpose of doing that is to identify the K and the beta independently. So that's the purpose of this. Sometimes they call it multi-rate testing. Okay, so that's why. So now you know, okay? And the point where you get significant deviation from Darcy, meaning that it is important, it's going to cost you money, so to speak. When this happens, there's an analysis of this in the book by Muscat, which I'll show you, using the analogy of a friction factor Reynolds number relationship for porous media. They just use the same equations, but instead of the diameter of the pipe, which I think is in the friction factor, and the Reynolds number, this is not my area. I think it's in both places. That diameter of the pipe is now some hydraulic diameter of the pore system. Now, the pores, it could be the diameter of the pores. They didn't use that because it's easier to measure the diameters of the grains, okay? Because they have this equipment that you probably find down in the cellar here to do that. They crush the rock and then they have like a sieve. It's like and they stack 10 of them together and you get different grain sizes, a distribution of grain sizes. So he basically took the average grain size, that's probably the 50% average grain size of a piece of rock to use instead of the diameter of the pipe. Okay, so the friction factor Reynolds number relationship. And I'll show you that plot here somewhere. I put it on the server if you want to look at it. Handouts, Muscat friction factor plot. Okay. Let's just try to do something here. Try to make this. It's kind of crooked, so if you do this, it's supposed to straighten it out. I don't know if it's going to. Yeah, kind of straighten it out. Okay, so this is the friction factor that's used by Muscat. And you can see it's got D for diameter here, pressure drop, and then it's got the velocity squared. So the friction factor is basically pressure drop over velocity squared. So let's just write that in the notes because I don't remember it. So friction factor is basically velocity squared on the bottom. Let's see here. So it's basically a measure of the pressure drop, but divided by velocity squared. And then the Reynolds number is defined down here as this kind of pore size, average pore size or grain size diameter, the velocity, and then it's got the density, I guess, should be, of the gas, and then and viscosity. So that's the Reynolds number definition. And I think these are both on the log scale. Why I'm drawing it when you have this nice picture. But basically, this should be a straight line for laminar flow, and then it kind of turns around like this for turbulent flow. Okay? And this delta P versus velocity translates directly into this kind of odd friction factor Reynolds number plot. But what they were looking for is kind of like when you had data, where did you seem to transition out of the laminar and into this, well, turbulent or whatever, non-Darcy type behavior. And this plot they took for a bunch of different porous media, both real rocks and probably some sands. I'm not sure, ceramic. Bradford sandstone is kind of a famous one. Ceramic A. Woodbine's a famous. Wilcox is famous. It paid my education. Let's see. So there's a bunch of different kind of stuff. Here's some just unconsolidated sands. And what you see is that where it's a straight line, and the slope of that is -1, I think. I'm not wrong. But when they came out here where some of these data, you started seeing the deviation. And basically that deviation, you can see it happening here. And this value of the Reynolds number is about 1, and this is 10, I think. 1 to 10. So somewhere between 1 and 10 is where you get the deviation. So basically this term here becomes important for a Reynolds number greater than about 1 to 10. Okay? And you can calculate, this if you've got it. In fact, Mike Vetkovich, when they discovered the Ekofisk field, which is oil, by the way, it doesn't have to be gas. It just has to be high velocity. Okay? So he actually took the pore sizes of chalk, which was found to be about half a micron, because the pore size distribution of chalk in the Ekofisk is from about 0.1 to 1 micron. That's it. Just one order. It's a very narrow distribution. So about a half micron, and they were producing at very high rates in the initial production test of Ekofisk. Okay, tens of thousands of barrels from a very limited interval. And he calculated, in fact, Reynolds numbers that were in excess of the 1 to 10 range. So he said, well, we should expect this effect going on for an oil well, and they did multi-rate test of the initial Ekofisk oil wells. Pretty amazing. Okay. is because he knew that, pipe flow, it doesn't matter if it's gas or liquid. Forchheimer's equation usually is applied to gas, but it applies to liquids if the Reynolds number is high enough. So you can just make a simple calculation. You have to find the average kind of grain diameter. Velocities you can calculate in the first 10 feet of the well. You can just take it, 1 foot out. So the radius is 1 foot. You get your velocity from your rate. Density and viscosity are just, you're now experts in PVT. So it's easy to calculate this number for any reservoir. And if you find that that number is greater than 1 to 10, then you should recommend doing a multi-rate test, because you could start seeing this effect. Yes?
The velocity we will put in this equation, it will be the core velocity or the Darcy velocity?
Oh man, I'm not supposed to ask questions like that. I don't remember. I should, but I don't remember. I think the paper is not all here. So let's see if it says here by chance. Velocity, rate of flow over cross-sectional area. So it's Darcy velocity. Now you could have used pore velocity, but it's Darcy velocity. It looks like from the labeling of the figure. Rate of flow over cross-sectional area. So, by the way, this is a very good example of how to do a good figure. You see how it's done? You got the cutout here. This is the legend. It's a very comprehensive legend because there's lots of data. You have to make it visible. Where do you put the legend? You don't put it like Excel lets you put it to the right or the top or the left. You put it inside the figure where it doesn't disturb the actual information. All the information is here on the left and the bottom. And you can see they cut away chunks of it that don't really matter. It's a very nice figure, as the technical figure goes. Okay, so it wasn't Muscat. He stole it from, no, he took it from Fancher, Lewis, and Barnes. I'm not sure. Pennsylvania State, some research center. Okay, so it's not only gases, but could be light oils, lower viscosity oils that are very high permeability. All right, so that's there's a paper around 1980. I don't know exactly what year, but around 1980, by the same cats I've been talking about, and a guy Firouzabadi, who's still alive. Firouzabadi, originally from Iran, he moved to the United States around 1980, and his first stop was in University of Michigan for about a year. And he worked with cats on a couple of papers that have become real classics. The one is on equation of state stuff, which you haven't heard about, but the table 5.2 is there. And then this other paper that they did on this high velocity flow in porous media. And they coined the term. They basically say that this is not turbulence. Physically, it's not turbulence. It's something else. And they don't quite know what it is, so they give it another name. They just call it high velocity flow effect. So they don't really say what it is, but it's not turbulence. So, but most of the industry called it turbulent flow before, or non-Darcy flow. But it's kind of a classic paper that tries to discuss some of the theoretical stuff. So you can look it up in the SP if you want. There's quite a few correlations that approximate the beta term as because it's a rock property, as a function of permeability and porosity. There's many correlations. None of them are really good. But I'll just mention that I think most of them have the form where it's approximately inversely proportional to permeability. So the higher the permeability, the lower the beta. I think that's the way most of the correlations look. Okay. Okay, so I'm going to cheat because, you know, I'm a little bit tired. I went to this fancy restaurant in Oslo last night, and it's like pouring me full of stuff. I'm not really here, it's totally functional. I don't dare try to derive completely the equation with Forchheimer. I probably could do it if you like put my life on the line, but I'm probably gonna, I'm just gonna drive it with Darcy, the Darcy equation for gas, okay? And then all of a sudden I'm gonna take the wand next hour and I'll say, and if we would have done this for the Forchheimer equation, it would look like this, okay? So, and then those who are interested in deriving stuff, you can do that over the Easter vacation as well. Actually take the, it's not that complicated, but I'm not gonna try to do it today. But what I am gonna do is I'm gonna take the Darcy equation for gas, because that will introduce an important concept regarding the driving potential average pressure minus PWF. Okay, because normally we can't just multiply by the pressure difference. And I want to go through why you can't do that, or when you can do that, and why you usually cannot use that. So, so just remember that the oil equation had this basically this J P average minus PWF, which for reservoir pressures that are greater than the bubble point, this is a pretty accurate equation. I mean, it's what you should use. So the rate is proportional with the difference in pressure. But for gases, only very special situations can you use this. Okay? So for gases, you may be able to use this when the flowing bottom hole pressure is greater than some big nut, when it's 5,000 psi, or probably 400 bar, let's say. I think Fetkovich uses a number 3,000 psi, so that would be 200 bar. Okay, so 300 bar. So if the bottom hole flowing pressure is greater than about 250 bar, you can use this as a reasonable approximation. That means, of course, the reservoir pressure is higher than that. Normally, the rate equation of gas is written differently. It's written as constant C, where we use pressure squared instead. Like that. Okay? And that would apply when reservoir pressure is less than about 150 bar. Okay? So the one condition is based on the bottom hole flowing pressure, and the other is based on the average reservoir pressure. Obviously, the bottom hole flowing pressure in the second case is going to be less than the reservoir pressure. Okay? So both of them are going to be low pressure. This is called low pressure approximation. And this is referred to as the high pressure approximation. And that's interesting because it's actually saying that gas is kind of behaving from a PVT point of view a little bit like liquid at high enough pressure. And that's a very important concept to take with you. And if you put gas in a pipeline at 300, 400 bar, it's going to behave like a liquid, like a light liquid. Okay? Probably have laminar flow and stuff. So it's a high pressure approximation, and then you get the low pressure approximation. But then the question is, what is the general equation? What's the general equation that treats everything? Doesn't matter. You don't have to say if, then, do this. Okay, so the general equation is where we want to get. And I'll just should I tell you, or should we derive it next? It doesn't really matter. Nobody's going to lose sleep. The problem is if I write it, I'm going to use terms that you won't understand. It'll just be another set of things you got to learn. New, okay, another pseudo. Remember, we got pseudo this, we got pseudo that. This is going to be another pseudo pressure. What the hell is pseudo pressure? We're going to talk about it after the break. But I'll go ahead and give you the equation. Basically the same C as this one here, but it's going to be pseudo pressure at average conditions and pseudo pressure at the flowing bottom hole. And that basically says that's for any PR range. Doesn't matter. Okay? So we'll talk next hour about what is this pseudo pressure and where does it come from. All right, let's go take a break.